Look closely at the periodic table. This grid functions as a highly predictable map, where every rule is driven by a single continuous tug-of-war. We call this tug-of-war effective nuclear charge, or Z-star. In this diagram, the positively charged protons in the nucleus pull inward on the outermost electron, but at the same time, the inner rings of electrons act as a shield, pushing outward. Calculate the difference between that inward nuclear pull and the outward shielding push, and you get Z-star, the true net force felt by that outer electron. Watch what happens as we move from left to right across a period. We add another proton to the nucleus and another electron to the exact same outer ring. Because the new electron doesn't add a new inner shielding layer, the shielding effect lags behind. The result? The net inward pull of the nucleus grows steadily stronger. Because that inward grip tightens with every step to the right, the physical volume of the atom shrinks. This atomic size is the baseline metric that dictates every other chemical property on the board. Now, let's look at the vertical axis. Moving from top to bottom down a group completely changes the math, because you are no longer adding electrons to the same outer shell. As you step down a group, the atom gains entirely new principal electron shells. Even though the nucleus is simultaneously gaining protons, these massive new spatial layers completely overwhelm that added charge. The ultimate rule for physical dimensions is that atomic volume shrinks from left to right and expands from top to bottom. Size dictates the behavior of the atom. The smaller the atom, the closer its valence electrons are to the nucleus, and the tighter they are held. Once you know exactly how tight that grip is, you can calculate the energy required to break it. That brings us to ionization energy, which is the exact amount of effort it takes to steal an outer electron. Because a smaller atom has a tighter grip, ionization energy acts as the exact inverse of atomic size. Warning tone. You would expect this energy requirement to rise in a perfect straight line from left to right across the table, but exam writers deliberately target the places where this straight line breaks. Look at this comparison of nitrogen and oxygen. Oxygen is further to the right, meaning it's physically smaller, but check their electron configurations. Nitrogen ends on exactly 2p3. Every orbital in the p subshell holds exactly one electron. That perfect symmetry provides immense structural stability. If you try to rip an electron away from that perfectly balanced arrangement, the energy meter spikes. It requires far more effort to break that stability and steal an electron from nitrogen than it does from the smaller oxygen atom. Always verify electron configurations before blindly applying the left to right size trend. Half-filled or fully filled subshells will always create an abnormal spike in ionization energy. We see similar complications with electron affinity. Instead of stealing, this is the energy an atom releases when it happily accepts a brand new electron. The halogens, which sit just one step away from a full shell, release the most energy. Fluorine is the smallest halogen, positioned at the top of the group. Standard logic dictates it should pull the hardest, and therefore possess the highest electron affinity. But fluorine has a spatial problem. Its 2p shell is incredibly small. When you force a new electron into that tight space, the existing electrons actively repel it. Now look at chlorine, right below it in the third period. It has a much larger volume, allowing the incoming electron to settle in smoothly without that intense repulsion. Extreme compactness causes repulsion. Because of this spatial limit, the third period p-block elements actually release more energy than their second period counterparts. Let's test this logic with a challenge. Try to order the physical size of nitrogen 3-, oxygen 2-, fluorine 1-, sodium 1+, and magnesium 2+. Notice that every single one of these ions possesses exactly 10 electrons. Since the electron count, and therefore the shielding, is equal across the board, the single differentiating factor is the nucleus. Count the protons pulling inward. As the positive charge increases from 7 up to 12, the inward tug-of-war gets stronger, and the actual radius shrinks sequentially from nitrogen down to magnesium. Isoelectronic series demonstrate how effective nuclear charge functions. When shielding is identical, the nucleus with the highest positive charge pulls most effectively. Look at practice question 23, asking for the halogen electron affinity order. The standard trend ranks spun straight down: fluorine, chlorine, bromine, iodine. But cross out that assumption. Due to the size paradox, chlorine accommodates the extra electron better. Swapping them makes option A correct. Mastering periodicity means anticipating where standard trends intersect with the physical, spatial limits of the atoms. This diagram serves as your final master map. It plots out exactly how atomic radius, ionization energy, and electron affinity shift across both the periods and the groups. As you trace these arrows, mentally overlay the high-yield exceptions we covered, like nitrogen's structural stability beating oxygen and chlorine's spacious volume beating fluorine. Focusing on the mechanics of effective nuclear charge replaces the need for rote memorization. When you can calculate the balance of protons and shells, the periodic table reveals its logic directly.